Okay, students, quick summary of what we have seen so far, right? So as you know, chemical kinetics is the branch of physical chemistry that deals with speed of a particular reaction, or you can say velocity of a particular reaction, the mechanism involved in it, and the factors which are going to determine the speed of the reaction, correct? Yes. Ranika, can you tell me what are the factors which determine the rate of a chemical reaction?
So the rate of reaction depends upon the concentration of reactants,
Yes, very good.
temperature,
Yes.
and nature of the reactions.
Nature of the reactants, right?
Yes.
Whether they are ionic or they are covalent, right?
Yes.
Ionic reactions are extremely fast. Suppose if the reactants are gaseous reactants, then even pressure will play a role, okay? And catalyst also plays a role, right? Okay, very good. Yes. Now let's consider this reaction. I think we have already learned this. I'm just revisiting them. Differential rate equation. All right. Now, suppose I consider a reaction, let's say. Right? P moles of A combining with Q moles of B, giving R moles of C and S moles of D. So the rate of the reaction can be defined in terms of the rate of disappearance of the reactants or in terms of rate of appearance of the products. So if you see, so the stoichiometric coefficients will be in the denominator. I hope you know that. And for the reactants, we will have negative sign because reactants concentration decrease with time. And for the products, if you see, we will not have the negative sign. It will be positive indeed because dC by dt is a positive quantity because concentration of products increase as time progresses in the reaction. More and more reactants convert to products. So products concentration will decrease and reactants concentration will decrease over time and products concentration will increase over time. Correct? Any doubts, Evelyn, at this point?
No, sir.
Now, the graph for the same we have seen, right? So let's say this is time and this is going to be the concentration of the reactant. Okay, let's say the reactant's concentration. I'll represent it with A, okay, in general. Or if you want, you can represent with R as well, no problem. So what is happening now? You can see that as time progresses, the reactant's concentration keeps on decreasing, isn't it? So if I take a slope, right, slope will be negative. Now, if I am talking about the concentration of the products, right, initially there is no product formed. As time progresses, more and more reactants convert to products, right? This is referring to product concentration, correct? And the point of intersection, that means where these two graphs meet, is a point of significance. Anybody can tell me what is this point going to be referring to? Yes, Evelyn, can you tell me?
Sir, equilibrium.
Equilibrium, exactly, right? It is the equilibrium. In equilibrium, rate of forward reaction will be equal to rate of backward reaction, right? Okay. Now, this is what we had learned in the first part, differential rate equation. So you may have questions like, they may give you an equation and ask you to write the rate, correct? And another thing is they may give you the rate of decrease of concentration of a particular reactant. They may ask you rate of appearance of a particular product, correct? So probably we could take up, we already solved a couple of questions based on this idea. Maybe just to revisit, we can do one question, okay? Yeah, probably you can see, right, how to write this equation. I think you can tell me what will be the answer for this question, students.
Excuse me, sir.
Yeah, Evelyn.
Sir, can you just explain why we are writing the stoichiometric coefficient as reciprocal, sir?
Yes, here it is like this, right? Yeah, if you see here, let's first look at the dependency, right? If I'm going to look at the dependency of a particular reactant, let's take an example. Let's take this example itself, right? What we have here. Okay, we have this reaction, right? 1 mole of hydrogen combining with 1 mole of iodine to form 2 moles of HI, correct? Now, if you see here, let us say we express the rate of a reaction. I think we have already learned that, right? If a reactant is converting to products, then we write the rate of a reaction as minus dA by dt. That we have established already, correct? So now, here what will be the rate of the reaction? In terms of, let's say, hydrogen, one of the reactants. What is it going to be? Can you tell me, Evelyn?
Sir, minus dH2 by dt.
Yes, minus dH2 by dt. That is already established, correct? Okay. Now, what does this signify? This signifies the rate of disappearance of hydrogen, isn't it? Now, you know that 1 mole of hydrogen combines with what? 1 mole of iodine to give 2 moles of HI, correct? At any point in time, if you see, right, by the time 1 mole of H2 is going to be disappearing, how many moles of iodine will be disappearing?
1 mole, sir.
Exactly. Exactly, right? So I will extend this to minus d by dt of I2, correct? Yes, Evelyn?
Yes, sir.
Right. Now, let's talk in terms of the formation of HI, right? Okay, now what does this represent, Evelyn?
Sir, rate of appearance of HI.
Exactly, right? Suppose if I take 1 mole of hydrogen, in the time that 1 mole of hydrogen is going to be disappearing, 2 moles of HI is formed, isn't it?
Yes, sir.
Correct? So if you see, can you tell me the rate of formation of HI with reference to the rate of disappearance of hydrogen? Suppose I'm giving, two sums on the board. One child is doing, let's say I'm giving 5 minutes. One child is doing that sum in 5 minutes. Another child is doing two sums in 5 minutes. So
Yes, sir.
whose rate of solving is, let's say A and B. A solves one question in 5 minutes. B solves two questions in 5 minutes. Got it?
Yes, sir.
So what is the rate of solving of B?
Sir, twice than that of
Twice as that of
A.
correct or not? Right? So
Yes,
the rate of formation of HI is how many times, Evelyn? In terms
twice
of
that
disappearance
of
of H2,
H2.
twice,
Minus 2 dH2 by dt.
isn't it? With a negative sign, of course, right?
Yes, sir.
So now if I am going to equate this here, right? So minus dH2 by dt must be equal to what? Simple math.
Minus 1 by 2.
Exactly. So this should be minus 1 by 2 dHI by dt. Is this clear to you now?
Yes, sir.
Yeah. So not minus, it's plus, correct? Because it's a product. So among the following, which is the right answer?
First option.
First option, of course, right? So I think it's clear now, right? Why it is so. So that's why we divide by the stoichiometric coefficient. Okay, let's move on to the other concepts which we have learned. In brief, we will look at them now. So we had seen about something called order of a particular reaction, correct? So order of a reaction tells us how much reaction rate is dependent on the concentration of the reactants, correct? So can you tell me what is order of the reaction, or a few points about order of the reaction? Yes, Evelyn, can you tell me what are few points on order of the reaction?
Uh, sir, Sir, order represents the dependency of rate on the reactants, like the number of reactants. Like if the order is 1, the rate depends on concentration of one reactant. And if the order is 2, it depends on the concentration of two reactants.
Not necessarily, not necessarily. Okay. Suppose there may be only one, let's say two reactants, but still the order can be one, right? And
Yes,
it can be like half also. It can be a
yes,
fraction,
sir.
right? Okay, good. So now order of a reaction is nothing but it's first thing that you need to know is it's an experimentally determined quantity. Can you please come on video, Evelyn, so that interaction can be comfortable? Yeah, Jerome, can you tell me one or two points on order, Jerome?
Some of the powers of the
Very good.
concentration of reactants, sir.
Very good. That is the most important definition, right? Sum of powers. Sum of powers of the concentration of the reactants in the experimentally determined rate equation. Right? Sum of powers of the concentration terms of the reactants in the experimentally determined rate equation. For example, if a reactant gets converted to products, or you can say rate law also, experimentally determined rate law. Okay. So then rate of the reaction can be expressed as A. Let's say two reactants are there. Let's say A and B. Okay. Giving P plus Q as products. Now rate is going to only represent concentration of reactants raised to some powers. Okay. Rate law does not relate concentration of products raised to some powers, right? It is only reactants raised to some powers. Okay. Let's say this is M, this is N. Okay. So you can see that the reaction is M moles of B combining with N moles of A to give P and Q. Okay. So the rate of the reaction is going to be given as a rate constant multiplied by concentration of the reactant A power X into concentration of reactant B to the power Y, where X and Y may or may not be equal to M and N. What is M and N? What are M and N? Yes, Ranika, what are M and N?
So as the number of moles of the reactants.
Stoichiometric coefficients. They're called what?
Stoichiometric coefficient.
Yes. And your X and Y need not be equal to M and N. Is that clear?
Yes.
Yeah. And how do we determine X and Y? We determine solely experimentally. What do you mean by experimentally? We keep the rate of a, we keep the concentration of a particular reactant same and change the concentration of another reactant and check how it affects the rate. Based on that, we'll be able to calculate what is the order of a particular reactant. Is that clear? Okay, good. And what else can you say, Jerome, about order? Any other point? Levin, please come on video now. Yeah, order can be a whole number or it can be a fraction. It can be 0, correct? So your order can be an integer, or a fraction. It can even be 0. And in very rare cases, it can also be negative. Okay, this is about order of a particular reaction. Now I was explaining to you, it is determined experimentally, correct? Based on experimental data, right? So we'll take up one problem to understand this concept, right? This also we have done it in the class earlier. Okay. Okay. Meanwhile, you can do this. Let me just, this is just based on the previous concept. You can complete this. Just take this down, students. Please note down the points in this question. So this is based on the previous concept. Have you got the answer? If you see the rate of the chemical reaction, from the equation, we are clear that it's going to be what? Minus 1 by 2 dSO2 by dt is equal to minus dO2 by dt, which shall be equal to plus 1 by 2 dSO3 by dt. I think that's clear, everybody. Yes, is it clear? Okay. Now what is given is the rate of disappearance of, in terms of O2, that is given. So we are given this value. It's 2.5 into 10 to the power minus 4 mole per liter per second. I think this unit is again very clear to you because mole per liter is molarity, the concentration. And per second refers to the dt which is there, time. Okay, fine. Now, we can see that this is directly related to rate. Therefore, rate of the reaction is equal to 2.5 to 10 power minus 4, correct? Now, what is asked is rate of disappearance of SO2 is asked. So that means they've asked you this, not this, only this, right? That is called rate of disappearance of SO2. So what we shall equate, we can equate these two. So minus 1 by 2 dSO2 by dt is equal to 2.5 into 10 power minus 4 units. Therefore, minus dSO2 by dt will be nothing but, you just have to take this to that side. So it is 5 into 10 power minus 4 mole per liter per second, which is the first option. Straightforward. Even without this, you can understand that SO2 disappears twice as fast as that of O2. Therefore, all that you need to do is just multiply this by 2, isn't it? Any doubts? Is it clear? Okay. Now we shall do a question on finding order of reaction, right? We'll do 2 questions on that. Straightforward. Okay, for reaction between A and B, producing C shows first order kinetics. First order kinetics means what? Order of the reaction with respect to A is 1. Second order in B, what is the meaning of that? Order of the reaction with respect to B reactant is 2. How can you write the rate equation? Can you tell me? Straightforward. Within a second, you can answer this. So rate of a chemical reaction is rate constant into A power X, B power Y, correct? Very clearly given to you. It shows first order kinetics in A. That means X value is 1. And second order kinetics in B. Therefore, the correct rate equation will be third option, KAB square. Yes, Jerome, what is the overall order of the reaction?
3, sir.
Exactly. It is nothing but the sum of these powers. 1 plus 2. So it's going to be 3, isn't it? Okay. What is the meaning of this, or how are we going to experimentally determine this equation? We'll see in the next question. Okay, you can see here. For a reaction A plus B giving products, what are we doing experimentally? We are doubling the concentration of A. And what do we observe? The rate of the reaction is doubled. Whereas when we double the concentration of B, rate remains unaltered. Then what is the overall order of the reaction? Instantly you can give the answer. At the same time, you can work it out and give the answer as well. So how do I write the rate equation, Ranika?
So concentration of A to the power of X into concentration of B to the power of Y.
Okay, is that all? Is it correct? Are you missing something? Jerome, what is Ranika missing?
Yes, sir.
K, exactly, rate constant, very important, right? Okay, now, so let's say this value is R, okay, rate. Now I'm doubling the, anybody can tell me the answer instantly? Yes, Evelyn, have you got the answer? No. Okay, Ranika, Jerome? Levin, come on video, ma? Yeah, good. Okay, ma. So now if you see, let's do it step by step, okay? The way you'll do it in your PU. And then I'll also tell you how you can do it mentally, okay? Fine. Rate of the reaction is getting doubled when I double the concentration of A. That means, let's say the new rate of the reaction, let me call it as R1, okay? Rate constant remains same, okay? Please remember, rate constant does not change if you change the concentration of any reactant. Rate constant is only disturbed when temperature changes. Okay. So here, Jerome, tell me, ma, which concentration am I changing?
A, sir.
A. I am doubling it, right? So instead of A, now what is the concentration?
2A, sir.
Very good. 2A. Correct. Okay. But B, I am not doing anything in the beginning. Okay. This is first equation. Okay. So this is experiment 1. The second part is experiment 2. Okay. Fine. Now, how can we find X? Very simple. What is happening to this rate, Jerome? Rate of the reaction is
Double, sir.
doubled. That means what? If this rate I am taking it as R, what this rate will be?
2R, sir.
Very good. So this is equation 1, this is equation 2. Let me now, if you want, I will rewrite it once or not required. We'll just do it now. So 2 divided by 1. I'm going to divide this first equation by the second. So K. Jerome, can I write 2A power X as 2 power X into A power X?
Yeah.
Yes. Please unmute and please be with me. Jerome, unmute, ma?
Yes, sir.
You unmute when I'm discussing with you. Okay. 2A power X, can I write it as 2 power X, A power X?
Yes, sir.
Yes. Okay, first equation is nothing but what? K into A power X into B power Y, correct? Second equation is 2R here and here it is R. Can you tell me, Jerome, what all get cancelled?
K and K, A power X, B power Y,
Yes,
and R, sir.
very good. So what is remaining now?
2 power X is equal to 2.
Yeah, 2 power X is equal to 2, isn't it? So we have 2 power X is equal to 2. 2 means 2 power 1. So from this, can you tell me, Jerome, what is X?
1, sir.
Very good. That's all. So this is what is called experimental determination. Correct? That may not be the final answer, correct? Or it may be the final answer that we don't know right now. Just because there are 2 reactants, we cannot expect that the order will be 2, right? So let's see. It all depends on this data what they have given, right? Now experiment 2. What is experiment 2? Take me through that, Jerome.
So you're doubling the concentration of B, sir, but rate remains unaltered.
Unaltered means in the second case also, what is the rate?
2R, sir.
In the second case, rate remains unaltered means
R, sir.
R only. Okay, correct. A I am not changing. Now what I am changing, Jerome?
B, sir.
B I am changing to what?
2B.
Exactly. Okay, this is 1, this is 3, let's say. Okay, Maranika, can you explain from here? What is my next step?
So then we have to divide 3 by 1, sir.
Yes. So what do you get? Come on. R by R is equal to K A power X. How can I write 2B power Y?
2 to the power y into concentration of V to the power y, sir.
Yeah, B to the power Y. Correct. Divided by K into A power X into B power Y. Tell me, Ranika, what all get cancelled?
K, A power x, B power y, and R, sir.
Yes. So what is it going to be on the left side?
1 is equal to 2 power y.
Okay. So what can you say 1 is? How can you write 1, Ranika?
2 power 0, sir.
Very good. 2 power 0 is 2 power Y. So what is Y?
0, sir.
Exactly. So what is the order of the reaction with respect to the reactant B? What is the order of the reaction with respect to the reactant B? Tell me, Ranika. We have just found, right?
0, sir.
Yes, tell me, Ranika.
0, sir.
0. Yes. What is the order of the reaction with respect to the reactant A?
1, sir.
Okay, can you tell me the overall order of the reaction, Ranika?
Rate is equal to
Not
K.
rate. No, not rate. Overall order.
Overall order is 1, sir.
Yeah. How is it coming 1?
So we have to add the powers, sir.
What are the powers going to be?
1 plus 0, sir.
Exactly. Okay. So the right answer for this question is 1. Correct. And now tell me, Ranika, how do you write the rate equation?
Sir, rate is equal to K, A raised to 1, B raised to 0, sir.
Yes. Even you can skip b raised to 0 because b raised to 0 is 1 only. Okay.
Yes.
That's all. That's how you write the rate equation. Correct. So the right answer for this question is first option. Is it clear, Evelyn? Okay. Jerome, Levin.
Yes, sir.
Yeah, good. Okay. I think we'll move on to the next concept, right? Now we have looked at differential rate equation. We have also looked at rate law, experimentally determined rate law. The third thing that we are going to look at is integrated first order rate equation. Very important question, right? So differential rate equation we have seen, rate law we have seen. Now we look at integrated rate equation. Okay. And what is of great importance is first order. You can always use it to derive for zero order, second order, etc. Okay. So integrated rate equation for the first order reaction. So first order reaction means what? Overall order of the reaction is 1. For convenience, we are taking that the reactant is 1. There is only one reactant. So let's consider a reactant A converting to products. Now, if you see, can you tell me the rate of the reaction in terms of differential rate equation, Evelyn?
So minus dA by dt.
Yes. Can you also tell me the rate expression based on experimentally determined rate law? Because it's clearly given here.
K into A power x.
Is it a power x or x we know already?
A 1.
It's 1 only, right? Because there are no more reactants. So there is only one reactant. So that's power must be 1. Yes, Evelyn, is it clear? Yeah. Now, because the LHS, the RHS is same, right? I can equate when LHS is same, so RHS also has to be equal. So I'm going to equate this now. Minus dA divided by dt is equal to K times A. Correct? Now we have to perform integration. For that, we are going to do from differential equations. You have learned a method called variable separable, isn't it? So what are you going to do? You're going to bring A here down, and dt you are going to shift it to the other side. Is it clear? So what are you going to have? Minus dA by A is equal to K into dt, isn't it? Okay. Now, what are we going to do now? Integration. K is a constant which can come out of the integration. Initially, we can use indefinite integral or definite integral. If you use indefinite integral, then you have to finally substitute boundary conditions. If you directly use definite integral, you can directly get the answer. Either way you can do. So initially time, let's take it as 0. And let's say at whatever time we are measuring, right? So let it be T. Okay. Initially the concentration of the reactant, let us take it as A naught. And finally, or at the time T, let us take the concentration as A. Obviously, A will be less than A naught, right? Because concentration of the reactant keeps decreasing, isn't it? Okay. Pranika, can you tell me what is the integration of dx by x?
Log x, sir.
Exactly, right? So now integration of dA by A, what will it be?
Log A, sir.
Yeah. So here, because minus sign is there, it's going to be minus log A. What is the base, Ranika? What is the base means? What number do you write here?
10, sir.
No. Okay. Throughout differentiation integration, when you perform integration or differentiation, it's natural logarithm. Okay. So it is E. Is that clear? Okay. So now upper limit is A, lower limit is A naught. Right. So now, Ranika, can you tell me what is the procedure once integration is over? What do you substitute? Upper limit?
Upper limit minus lower limit, sir.
Yes, yes. So on the right side, if you see, it is k into, what is the integration of dt?
T, sir.
T, correct. And lower limit is 0 and upper limit is t itself. So now, when I substitute the lower limit, upper limit first, it is minus log a, minus of, and one more minus sign is there outside, so it will be plus log a naught is equal to k into t minus 0. So second part I am leaving it. Now tell me one thing. What is log m minus log n? Yes, Ranika?
Log M minus log N, sir. Log M by N.
Yes. So here it is like log a naught minus log a. So it will be log a naught divided by a. And still the base is e. Correct. So now one more way of writing this, right, is, change of base rule, right? Evelyn, can you unmute now?
Yes, sir.
So can you tell me, Ma, if I think you know this, how do I write a naught by a?
Sir, e power kt.
Very good. That is called change of base rule. So a naught by a can be written as e power kt, or if I take reciprocal of this, right? A by a naught is equal to e power minus kt, or in other words, a is equal to a naught into e power minus kt. This is a very famous equation which is also used in nuclear physics, okay, radioactivity, okay. All radioactive reactions are first order reactions. They follow first order kinetics, okay, that's important to know, okay. So if you see radiocarbon dating, you might have learned both in biology as well as in physics. So it's that's calculated based on this equation, right? A naught is going to be the initial amount of substance present after time t. You know that the substance decays, right, because of radioactivity, and this is the substance which is left, right? Okay. Anyways, now this is important for your numericals. And now let's look at a final expression here. So Ranika, initially we were mentioning that the base is 10, right?
Yes, sir.
Yeah, base is obviously not 10 because whenever you do integration or differentiation, what is the base?
The natural logarithm
Natural
E.
logarithm, right? But always it is convenient to use common logarithm, which is base 10. So what we are going to do is we are again going to do change of base rule here. So how can I do that? This I can write it as log 10 to the base e into log a naught by a to the base 10. So what have I done? It's like multiplying log 10 and dividing log 10. That's the meaning, right? So this way, what was in natural logarithms, I have now converted to common logarithms. And this number has a particular value. You can check in your logbook. Log 10 to the base e, it is 2.303, right? Log e to the base 10. Okay, we are going to, let me write it here. Let me write it. Okay, no problem. So Kt is equal to 2.303 log A naught divided by A to the base 10. This is the integrated rate equation, very important for solving numericals as well as for your PU. This is an important question, okay, amongst others. Okay. From this, you can also find, your T or K. So T can be written as 2.303 divided by K log of A naught by A. This is the integrated rate equation for your first order reaction. Very important question. Okay, I hope you have noted down, or I'll just give you a couple of minutes. Please go through it once. Let me know if you have some doubts. Students, quickly we'll do a revision of the whole thing now. Yeah, just observe this question, students. So I was telling you how you can calculate mentally, right? So here for a reaction A plus B producing products, doubling the concentration of A, keeping B's concentration constant, rate of the reaction is getting doubled, right? Just, visualize this. No need, see here in competitive exam, no need to do the solving, right? Just mentally you can do it. If you, once you catch it, it's very simple. So here I'm doubling the concentration of A, reaction rate is doubling, which means doubling means there is a 2 on the right side, right? 2 power what is going to be 2 ma? Yes, Evelyn?
1.
1, that's it. So order of the reaction with respect to concentration of the reactant A is 1. Yes, now, Jerome, I'm doubling the concentration of B, keeping A as it is, right? There is, rate is not impacted, rate is unaltered. Rate is unaltered means on the left hand side, what is the number I'm having? Or simply understand, I am changing the concentration of B, but there is no effect on the rate of the reaction. So can I say that rate of the reaction is independent of concentration of B? Unmute, Jerome. Yes, no? I doubled the concentration, but I did not see any effect. That means it's independent. Ranika, if it is independent, right? If rate is independent of a particular reactant's concentration, what is the power?
0, sir.
Exactly. That's all. Instantly you can answer, right, without writing all these things for your competitive exam. So for reactant A it is 1, for reactant B it is 0. 1 plus 0, 1 is the overall order. That's it. As simple as that, right? So let me give you one question. Tell me what would be the answer, right? I'll ask you individually. Yes, Evelyn, first, Ranika, you can answer first.
Yes, sir.
Okay. I am doubling the, let's say there are 2 reactants, okay, A and B. I am doubling the concentration of A, okay?
Yes, sir.
It is becoming 4 times. What do you expect the rate, order of the reaction with respect to that reactant?
So what is becoming 4 times?
Rate, reaction rate.
Okay, sir.
The concentration I am doubling for a particular reactant A, doubling, but then the reaction rate becomes 4 times.
Sir, X is equal to 2, sir.
Very good. That's all. That's all I wanted, right? So order of the reaction with respect to that reactant is 2, because when I'm doubling, that means right hand side I have a 2, but left hand side rate becomes 4. That means what? 2 power x is 4, and for x is 2. That's it. Is it clear, Evelyn?
Yes, sir.
Jerome, clear?
Yes, sir.
Enoch.
Yes, sir.
Okay. Now, let's say I'll ask Enoch now a question.
Yes.
If I'm tripling the concentration of a particular reactant, okay, tripling the concentration of a particular reactant, and my rate becomes 27 times, what is the order of the reaction with respect to that reactant?
Sir, 3 times.
3 times, exactly. Because 3 power 3 is 27. Very good. All right. Okay. Now, Evelyn, one question to you. Slightly challenging question. Try, and everybody can also try this. I'm doubling the concentration of a particular reactant, and the rate becomes 1.414 times.
The root 2. It's half, root half.
Very good, Enoch. Perfect. Because on the right side I have 2 power x. On the left side it becomes root 2. Root 2 is nothing but a 1.414, right? That's 2 power half. So therefore x is equal to half. Very good. Now one more question. I triple the rate of a particular reaction. Rate of the reaction becomes 1.73 times, 732 times. What is the order of the reaction with respect to that reactant? I'm tripling the rate of reaction, and rate becomes tripling the concentration of a particular reactant, and the rate of the reaction becomes 1.732 times. Yes, Makvik, same idea. What is 1.732?
Same thing, sir. Root 3.
Root 3, right? So 3 power half. So once again, the answer is half. Okay, very good. Fine. So now integrated rate equation, one quick review. So A is converting to products. Rate of the reaction, you know that you can write it as minus dA by dt using differential rate equation. And using rate law, you can write it as rate is equal to K times A power 1. Why do you write 1? Because it's first order reaction. Now, because LHS is same, you equate the RHS. Minus dA by dt is equal to Ka. So you do variable separable. You do minus dA by A is equal to K times dt. Initially concentration of reactant is A naught. After some time it reduces to A. Initially time is 0. After some time it becomes T. So when you integrate dA by A, it becomes log A. And always remember, when you integrate or differentiate, it is natural logarithm is what you're going to get, right? Now, upper limit minus lower limit. So that's going to be minus log A, minus or minus plus log A naught is equal to KT. So log M minus log N is log M by N, correct? So A naught by A is equal to e power KT. If you take reciprocal, it will be A is equal to A naught into e power minus KT. This is very useful for nuclear reactions, radioactivity. All radioactive reactions are first order reactions. They follow first order kinetics. Okay, that's for your questions in physics which you can answer. Okay, but anyways, from chemical kinetics perspective, you have log E, but you have to convert into log 10, right? That's common logarithms. For that, you need to multiply this factor log 10 to the base E. This is called change of base rule. Now log 10 becomes, the value is 2.303. So KT is equal to 2.303 log A by A naught by A, or T is equal to 2.303 by K log A naught by K. We have seen half-life period. So half-life period means nothing but the time it takes for a particular reactant to become half its concentration. Suppose initially you start with 100 mole per liter. For it to become 50 mole per liter, it takes one half-life. Okay. So how are we going to find that? Initially time is 0. At that time the concentration of the reactant is maximum A naught. When time t is equal to 1 half-life period, the concentration of the reactant at that time becomes half of what it was before. So wherever A is there, you substitute A naught by 2. A naught gets cancelled. 2 comes to the top. Log 2 is 0.3010. You get 0.6931 divided by K. That is your half-life period, right? So all these are very important aspects. Right, now next, few more concepts are there in your chemical kinetics, which are again very simple. So the next concept that you have is what we call as molecularity of a reaction. Okay, so what is the meaning of molecularity? So molecularity in simple terms means the number of molecules which are involved in the reaction, in a given reaction. Okay, and we can always say molecularity for a simple reaction. Okay, that means if it's a complex reaction, what is a complex reaction? A reaction which proceeds in multiple steps. All right, now for a simple reaction we can say molecularity, right? Molecularity is about actually what happens. It's about the mechanism of the reaction. So a complex reaction actually happens in several steps. In each step there may be one reactant involved. It may be like dissociation of a particular reactant to give products, or it may be two reactants involved. Okay, two molecules of the reactants come and collide with each other at a particular angle and they form products, right? So in that case, when two molecules are involved in the collision process to form products, then you call as molecularity of that reaction to be 2. In some special cases, you may have three molecules coming together and colliding and forming products. So molecularity may be 3, but usually molecularity is never more than 3, right? Because practically it is not possible that simultaneously you have 4 molecules coming and colliding with each other and forming products. So usually molecularity is nothing but what? Number of molecules of the reactants coming together to form the product in a simple reaction or a single step reaction. Correct? Okay. So usually common question asked is what is the difference between order and molecularity, right? So right? Order is nothing but sum of powers of the concentration terms of the reactants in the experimentally determined rate law. Molecularity is a whole number. It talks about the number of molecules colliding simultaneously to form products, right? Molecules of the reactants. Now, molecularity can be a whole number. It can only be a whole number, right? Like 1, 2, or 3, right? Whereas order of a reaction can be 0, fraction, a positive integer, or even it can be negative in rare cases. All right. So these are some of the things which are asked. So molecularity is basically it refers to the number of molecules. Just as a layman, you can understand this. And for specifically when you write definitions, I want you to be exactly repeating what is there in the text. Okay. Number of molecules colliding, or you can say involved in a number of molecules of the reacting species, or I can say reactants. Simple or a single step reaction. For a multi-step reaction or for a complex reaction, you cannot say this is the molecularity. It doesn't make sense, correct? Molecularity is always expressed for a single step reaction. So if it's a complex reaction, let's say which involves 3 steps, you will write each of those 3 steps, and for each single simple step, you will tell the molecularity. Is that clear? Right? Okay. Now, it's always a whole number. It's 1, 2, or 3 usually, right? And it can only be computed for a single step, simple reaction. Okay, now I'm going to tell you something here, right? Couple of points I'm going to give you, which will be very important. If the reaction is a single step reaction that we are talking about, then for that reaction, your order and molecularity will be same for that reaction. Usually, I can say again, order and molecularity will be same for a simple single step reaction. All right. Point number 2. For a complex reaction which has many steps, your order will be determined based on the slowest step in the mechanism of the reactions. Let's say a complex reaction is there. It involves 3 steps. The first step is very fast. Third step is very fast. But second step is very slow, right? Then the slowest step determines the rate of the reaction, isn't it? Suppose 3 of you at home, you are planning to go to a movie. Let's say, whether you reach on time or whether you start on time depends on what? Who gets ready the first or who gets ready the last? Yes, Jerome. Unmute.
Yes, sir.
Who determines whether you will leave home to reach the theater in time? The one who gets ready earliest or the one who gets ready the slowest?
The slowest, sir.
Slowest, right? Anyways, the one who is ready has to wait for the slowest, so that all of you can go together, right? So slowest person determines the time at which you will start or you will reach, correct? Similarly, in a reaction, if it's a 3-step reaction or 4-step reaction, the rate of the reaction is determined by the slowest step. Therefore, the slowest step is called rate determining step. All right? Okay. And for the slowest step, if you see, whatever is the molecularity of that particular slowest step, That will be the order of the overall reaction. Is that clear? So these pieces of information will help. Okay. Fine. Now, okay. Next idea that you can have is pseudo unimolecular reactions. Okay. Okay. Can you give me an example for a pseudo unimolecular reaction? Okay. What is the meaning of that? Okay. So here it may be let's say a single step reaction. I'm going to write it for you. A plus B gives C plus D. Right? Usually, if it's a single step reaction, right, then rate of the reaction will be, in fact, the product of concentration of the reactants raised to the stoichiometric powers itself. That X and Y will be 1 itself if it's a single step simple reaction. Okay, because for this reaction molecularity is 2 and order is also 2. Okay. However, if I take one of the quantities in large excess, right? If I take one of the quantities concentration in large excess, then change in concentration of the reactant is going to be, of that reactant is going to be very, very small, isn't it? For example, according to this reaction, 1 mole of A combines with 1 mole of B to give 1 mole of C and 1 mole of D. Suppose instead of taking few moles of B, I'm taking 1 lakh moles of B, right? Then what will happen? 1 mole of A will still react with 1 mole of B only, right? How many moles of B will be left, remaining unreacted? Let's say 99999, correct? So earlier it was 1 lakh, now it is 99999. So the difference is negligible compared to how much is the quantity, right? It's 1 upon 1 lakh, right? So the rate of the reaction will hardly depend on your concentration of B in that case, when you take one of the reactants in large excess. So although it's a bimolecular reaction, because I am taking one of the reactants in large excess, it becomes a reaction which only depends on one of the concentration of one of the reactants. And that's why you call these reactions as pseudo unimolecular reactions. Because you're taking extraordinarily large proportion of one of the reactants. We'll now look at effect of temperature and effect of catalyst. Okay, effect of temperature on the rate of the chemical reaction. Basically, your rate constant value is immune to change in concentration of the reactants, right? If you change the concentration of reactants, rate constant will not change, but rate will change, correct? Usually when the concentration of the reactants decreases, rate of the reaction also decreases. But rate constant remains undisturbed, isn't it? But rate constant depends on temperature. So as a thumb rule, for every 10-degree rise in temperature, for every 10-degree rise in temperature, rate constant usually doubles. In some cases, it triples. Okay, this can be helpful. And there is an equation which actually governs this effect of temperature. Okay, I'm going to show that equation to you now. One second, students. So usually if you see, right, in this example, see this question. Rate law for the reaction sucrose combining with water in the presence of in an acid medium to give glucose and fructose. I'm sure you have learned this equation, right? C12H22O11 combining with water to give C6H12O6 for glucose and C6H12O6 for fructose. Correct? You have learned this equation, correct? Usually what we do is we take water in large excess. It's a single step reaction. If you observe here, you may think that it is bimolecular, right? But this is a typical example for a pseudo unimolecular reaction. So you may think the answer is first option, right? Rate law is K into sucrose power 1, water power 1. But that's not true because you take water in large excess, sucrose power 1. It only depends on the concentration of, the rate of the reaction only depends on the concentration of sucrose and not that of water. Because you're taking water in large excess in this particular reaction. Okay. Now, okay. I'll send you this worksheet. Please do try this worksheet, everyone. Okay. Yeah. So this is the equation which I was talking about. So effect of temperature on rate constant is well explained using an equation called Arrhenius equation. Especially this concept is more important for your competitive. Okay. So this is the equation. So rate constant K is equal to A e power minus E by RT, where A is a constant, E is your Napier's number, what you use in your logs and in mathematics. Power minus E. E is called activation energy. We'll talk about it now. Divided by RT. RT is something which you already know, right? Temperature, absolute temperature and molar gas constant, right? So here if you see, now which of the following does not represent Arrhenius equation is one of the questions. So this is of course the right, right expression. So that's not the correct answer for this. If you take log on both sides, then you will get this expression. Then if you convert from log E to log 10, you'll get this expression. So all these three are representing Arrhenius equation. This is the one which is not going to represent. But this basically tells you about dependency of rate constant on temperature. Okay. So as a thumb rule, you can remember for every 10-degree rise in temperature, your rate constant usually doubles. Okay. Next, let's talk about a little bit about your effect of catalyst. Okay. So all of you have learned that, catalyst basically, let me just, in simple words, I'll explain this.
So in the previous equation,
Yes,
sir, in the previous question, sir,
yeah,
when you took log on both sides, no?
yeah,
The A into E,
yeah.
shouldn't that be log A plus log E?
See, 1 minute, ma. Let me write the equation here. Correct, Enoch?
Yes, sir. Log AB is equal to log A plus log B, no, sir?
Yes, ma. Log K is equal to log A plus log E power minus EA by RT. Correct, Enoch?
Yes, sir.
So log K is equal to log A plus K. Using power rule, I can bring it to the front. I can bring it to the front, right?
Yes, sir.
So what does this become? Minus EA by RT into log E, correct?
Yes.
All these bases are E. Can you tell me what is log E by log E to the base E?
Oh, it will be 1.
That's why you have this expression. Yeah, did you understand this now?
Yes, sir.
Yes, okay. Good. Okay, now let's come to catalyst, right? So what is catalyst used for? We have learned in our lower classes, right? Catalyst, a positive catalyst is one which will speed up a particular reaction, isn't it? Correct or not? Right? Okay, now how exactly does it do? How exactly does a catalyst bring down the rate of speeds up the reaction is, say for example, it's best explained using something called activation energy. I will just tell you about that. In simple words, let's say this is your energy profile. Okay, now if you see, let us say the reactance energy. Reactance energy is somewhere here, okay? Let's say. Now let's say to form the products, let's say product energy is somewhere here, or probably, let's say it may be an endothermic reaction or an exothermic reaction. So let's say we have reactants here, reactants concentration, not concentration, energy profile, energy. Products energy here, okay? Now, usually what happens is reactants don't get converted to products directly. Usually they form an intermediate whose energy is high and it's unstable. Then it lowers its energy to provide products, right? Usually. So this is the usually energy of the intermediate. All right. So now what happens is your already the energy possessed by the reactants is there. But then how much more do they need now in order to form products? This additional energy they require, correct? And this energy is called energy of activation. Okay. So now if I provide that energy, right, then what, or if that energy is generated in the system itself, then what will happen is that intermediate will form and then you will have products form. So two reactants come in collision and then they have sufficient energy so that they form the intermediate and then finally it becomes the product, right? However, then you call it as an effective collision, okay, which forms products, right? Suppose if the energy that the reactants are going to possess while they collide is not going to be sufficient to form the intermediate, right? Whether this energy of activation energy is not there, then what will happen is products won't be formed. It will be an ineffective collision, right? Now what happens is, in order to attain that activation energy, right? Not all reacting molecules or not all colliding reactants will have that energy. That's why formation of products takes more and more time, right? However, if I have a catalyst, right? What does a catalyst do? It involves in the reaction and then it comes back as it was originally, right? At the end of the reaction, correct? So maybe in much lower class, you might have seen, right? Catalyst, does not participate in the reaction, but that's not true, right? It participates in the reaction. It helps in formation of the intermediate, and then it anyways is regenerated back at the end of the reaction. Now, more importantly, what does it do? It lowers the activation energy. So catalyst, how does it speed up the reaction? It lowers the energy of activation. So what does it do? It's going to provide an alternate path for the reaction to proceed, right? So a new activation energy is needed in the presence of your catalyst. So now this is your EA, correct? EA new. You can see that your EA dash is less than EA, correct? Which means the catalyst presence has reduced the additional energy that is required by the reactants to form the products. Now, because it is a smaller peak to rise, smaller peak to climb, right? It becomes easier for more reactants to result in effective collision, right? This is the concept of catalysts, right, students? So these are the very important aspects which is being covered in this particular chapter, right? Any questions until this point, students?
So, how does it lower the activation energy?
Okay, that's based on the you have to go into the mechanism of the reaction. Each reaction it will be different. So basically, you can understand that the intermediate that is formed, right now, in this case, in the presence of your catalyst, a different intermediate will be formed, whose energy profile will not be that high. So in this case, let's say you are having intermediate 1. Here you have intermediate 2, let's say. The intermediate 2 is not going to require EA energy. It's going to require, let's say, EA1, which is lower than what it requires initially. Does it make sense,
Yes.
Yeah, in some cases, your catalyst is going to provide more surface area, and because of that, it's going to, the reaction is going to proceed further. But this is the lowering of activation energy concept. Yeah. Yes, Evelyn, any questions?
No, sir.
Okay, Jerome?
No, sir.
Yeah, Ranika?
No, sir.
Okay, good. Right. So I will just share the worksheet with you. So you can also attempt the worksheet. And please, whatever doubts you may have as you solve and as you do your NCRT questions as well, please get back to me, and we can connect during the week or even later for your doubts. Right. So even tomorrow is also okay if you want your doubts to be clarified. Please be in touch with me. Okay. So all the very best, students.
Thanks, sir.
Is there any other topic that you want me to address, Evelyn?
No, sir.
Yeah. So this concludes our syllabus in chemistry as well, right? So I wish you all the best. Please prepare for your exams very well, students. All the best, and please stay connected. And from Jan, we'll be scheduling some tests for you guys on MCQs. We'll discuss them, and so that you are prepared, right, for your PO also. This time PO also, you have a new pattern, isn't it? Where we'll have assertion reasoning, and whatever is the pattern, based on that, we'll have questions which we'll discuss in the month of Jan and Feb, based on your academic schedule in the school. Okay, all the best. Good night, take care.
Thanks, sir.
Thank you.
Thank you.
Bye, students.